In this set of solved problems, we consider various applications of the fundamental theorem of calculus. Let us start by recalling the properties of integrals of continuous functions. Integral from c to c of any continuous function f is always 0. This follows since the length of the integration interval is 0. The integral from a to b of f of x dx is always negative of integral from b to a f of x dx. That is, if we switch the bounds, also the sign of the integral changes. The third property is that integral from a to b of a continuous function f is the same as integral from a to c of f plus integral of c to b of f. Fourth property, integral from a to b of a constant r times a function f is same as r times integral from a to b of the function f. The last property says that integral from a to b of the sum of the functions f and g is integral from a to b of f plus integral from a to b of g. So the integral of a sum of functions is the sum of integrals. The following table of indefinite integrals is useful in computations. It has been obtained by the corresponding table for derivatives. The first rule says that the indefinite integral of x to a power r dx is x to a power r plus 1 divided by r plus 1 plus the constant of integration, and this assuming that r is different from negative 1. If r equals negative 1, then r plus 1 is 0 and we cannot divide by it. The second rule says that the indefinite integral of 1 over x is log of x plus a constant c1 if x is positive, and log of negative of x plus a constant c2 if x is positive. This is usually written as saying the indefinite integral of dx divided by x is log of absolute value of x plus a constant of integration. This constant of integration is not really a constant, it is only a constant on each interval of definition of the function to be integrated. In this case, these intervals are x greater than 0 and x less than 0. The third rule says that the integral of a constant function is constant times x plus constant of integration. The fourth rule says that integral of sine is negative cosine plus constant of integration. Fifth rule says that integral of cosine is sine plus constant of integration. Sixth rule says that integral of e to the power x is e to the power x plus constant of integration. Seventh rule says that integral of a to the power x dx is a to the power x divided by natural logarithm of a plus constant of integration. Here a is greater than 0 and different from 1. If a equals 1, then a to the power x is the constant function 1. The eighth rule says that integral of 1 divided by 1 plus x squared is arctangent of x plus constant of integration. Ninth rule says that integral of 1 divided by square root 1 minus x squared is arcsine of x plus constant of integration. 10th rule says that integral of 1 over cosine squared of x equals tangent of x plus constant of integration. And the 11th rule is a general rule which says that the integral of the function a times f of x plus b times g of x, where a and b are constants, is a times integral of f of x plus b times integral of g of x. This is true for all constants a and b. The fundamental theorem of calculus says that if f is a continuous function, then the function capital F, which is defined by setting capital F at x equals definite integral from a to x f of t dt. That this function is an antiderivative of the function small case f, that is capital F prime of x equals small case f at x. Conversely, if capital F is any antiderivative of the function small f, then the definite integral from a to b f of x dx equals capital F at b minus capital F at a. The fundamental theorem of calculus says that if f is a continuous function, then the function capital F, which is defined by setting capital F at x, equals definite integral from a to x f of t dt. That this function is an antiderivative of the function small case f, that is capital F prime of x equals small case f at x. Conversely, if capital F is any antiderivative of the function small f, then the definite integral from a to b f of x dx equals capital F at b minus capital F at a. The problems to be considered are the following. First, use the definition of the area of a domain under the graph of a given function to compute the area of the domain under the graph of the function y equals x cubed for x between 0 and 2. In the second problem, we have to compute the limit as n goes to the infinity of the sum k from 1 to n k squared over n cubed by interpreting this as the area of a known geometric figure and then by computing the area of this figure. In the third problem, we have to estimate the value of the integral from 0 to pi over 2 sine of x dx by computing estimates with 5 subintervals. In the fourth problem, we have to express the limit as n goes to the infinity, sum k from 1 to n, square root n squared minus k squared, and that divided by n squared. We have to express this as an integral. In the fifth problem, we have to estimate the integral from 0 to 1 of square root of 1 plus x squared. And we have to show that this number is between 1 and square root of 2. In problem 6, we defined the function capital F by setting capital F at x equals integral from x to x squared of sine of t divided by t dt. And our task is to compute the derivative of this function capital F. In the seventh problem, we ask what is wrong in the following computation of the definite integral from negative 1 to 1 of dx divided by x squared. And the computation goes that the integral from negative 1 to 1 over x squared dx, is of course the same as integral from negative 1 to 1 of x to the power negative 2 dx. And an antiderivative of x to the power negative of 2 is x to the power negative of 2 plus 1 divided by negative 2 plus 1. And we substitute to this from negative 1 to 1. So we get to substitute to minus 1 over x from negative 1 to 1. And the substitution yields the value negative 2. So what is wrong here, if anything? In problem 8, we assume that the function small f is continuous, and that integral from 0 to x squared f of t dt is e to the negative x squared. We have to compute f at 1. In the ninth problem, we have to compute the limit as x goes to 0 of the fractional expression integral from 0 to x sine of t squared dt divided by x cubed. Using the definition of the area of a domain under the graph of a given function, we have to compute in this problem the area of the domain under the graph of the function y equals x cubed for x between 0 and 2. We have to do this by the definition of the area. And the area was defined by decomposing the interval in question into subintervals. Now we decompose the interval from 0 to 2 into n subintervals of equal length. On each subinterval we place the rectangle shown in this picture. The height of the rectangle is the value of the function y equals x cubed on the right endpoint of the subinterval in question. Hence, for the kth subinterval, the right endpoint of the subinterval is 2 times k divided by n. The value of the function at that right endpoint is 2 times k divided by n cubed. That is the height of the kth rectangle. The width of the rectangle is 2 divided by n, therefore the area of the rectangle is 2 times k divided by n cubed times 2 divided by n. We take the sum of these areas as k goes from 1 to n, and this is our approximation for the area under the graph of the function y equals x cubed. So the right sum approximation for this area is therefore summation k from 1 to n, 2 times k divided by n cubed times 2 divided by n. Here 2 cubed times 2 is 16, that can be taken outside of summation, and in the denominator we have n to the fourth, and that can also be taken outside of summation. So the right sum approximation is 16 divided by n to the fourth times sum k from 1 to n k cubed. And now this sum k from 1 to n k cubed is n to the fourth divided by 4 plus n cubed divided by 2 plus n squared divided by 4. This we have seen before. We conclude that the right sum approximation for the area of the domain under the graph of the function x cubed and over the interval from 0 to 2 is 16 divided by n to the fourth times n to the fourth divided by 4 plus n cubed divided by 2 plus n squared divided by 4. We expand the product and we get that the right hand approximation is 4 plus 8 divided by n plus 4 divided by n squared. And we now let n go to the infinity and obtain at the limit the number 4. And we conclude that the area of the domain under the graph of the function y equals x cubed and over the interval from 0 to 2 is 4. In this problem we have to work backwards from Riemann sums to domains and to areas of domains. Our task is to compute the limit as n goes to the infinity of the sum k from 1 to n, k squared over n cubed, by interpreting this as the area of a known geometric figure and by then computing the area of this figure. So we must relate this sum with a sum approximating the area of some domain, preferably of some domain under the graph of a function. To that end, we observe that sum k from 1 to n, k squared over n cubed, is of course the same as sum k from 1 to n, k over n squared times 1 over n. And this sum is the combined area of the green rectangles approximating the domain under the graph of the function y equals x squared and x between 0 and 1. So now when we take the limit as n goes to the infinity, we obtain at the limit the area of the domain under the graph of y equals x squared and x between 0 and 1. This area is the definite integral from 0 to 1 of x squared dx. That is a substitution from 0 to 1 to x cubed over 3, because x cubed over 3 is an antiderivative of x squared. And this substitution yields 1/3. But we already knew by previous computations that this area is 1/3. Hence even integration was not really necessary. And we conclude that the limit as n goes to the infinity of the sum k from 1 to n, k squared over n cubed, is 1/3. In this problem we have to compute left, right and middle point sums for the integral from 0 to pi over 2 sine of x dx with 5 subintervals. That is, we have to compute the numeric approximations for this integral from 0 to pi over 2 of sine of x dx with 5 subintervals. The division points are 0, pi over 10, 2 times pi over 10, 3 times pi over 10, 4 times pi over 10 and 5 times pi over 10, which is pi over 2. When we divide the interval from 0 to pi over 2 to 5 subintervals of equal length, then the length of each subinterval is pi over 10, and from that we get these division points. The left approximation is now the combined area of the rectangles over these subintervals, where the height of the rectangle is the value of the function at the left endpoint of each subinterval. Therefore, the left approximation with 5 subintervals is sine 0, that is sine at the left endpoint of the first subinterval, times pi over 10, plus sine pi over 10 times pi over 10, and so forth, and finally sine 4 times pi over 10 times pi over 10. That is the combined area of the 5 rectangles placed over the subintervals and computed with height being the value of the function at the left endpoint of each subinterval. The numeric approximation of this sum is 0.8347. The right approximation computes slightly higher rectangles, where we evaluate the function at the right endpoint of each subinterval. The right approximation with 5 subintervals starts sine pi over 10 times pi over 10 plus sine 2 times pi over 10 times pi over 10 and so forth, and the last term of this is sine pi over 2 times pi over 10. The numeric approximation of this is 1.1488. In the middle sum approximation, we place over each subinterval a rectangle whose height is the value of the function at the midpoint of this subinterval in question. Therefore, the midpoint approximation is sine pi over 20 times pi over 10 plus sine 3 times pi over 20 times pi over 10 and so forth. The last term is sine 9 times pi over 20 times pi over 10. And the numeric value of this is approximately 1.0041. So we estimated the integral from 0 to pi over 2 sine of x dx. That is the area under the graph of the function sine of x between 0 and pi over 2. The left approximation which we computed was approximately 0.8347, and that is the combined area of the green rectangles shown in this figure. The combined area of the green rectangles is fully included in the area of the domain under the graph of sine of x, and something is left out. Therefore, this left approximation is going to be less than the actual area of the domain under the graph of sine of x. The midpoint approximation is already pretty good. Here we leave out some parts of the domain, but then we take some extra parts which compensate partly what we left out. And the right approximation computes the combined area of rectangles whose height is the value of the function at the right endpoint of each subinterval. The union of these rectangles contains completely the domain under the graph of the function sine of x. Therefore, the combined area of the rectangles is certainly larger than the area of the domain under the graph sine of x. Now this follows that the function sin of x is increasing on the interval of integration, therefore the left approximation is going to be less than the actual area, and the right approximation is going to be more, and the middle point approximation is the best one of these three approximations. Now the integral from 0 to pi over 2 sin of x dx can easily be computed by the fundamental theorem of calculus. Negative cosine is an antiderivative of sine, therefore the integral from 0 to pi over 2 sin of x dx is substitution from 0 to pi over 2 to negative cosine of x. And that is negative cosine at pi over 2 minus negative cosine at 0. Cosine at pi over 2 is 0, and then we had minus cosine at 0, which is 1. Therefore we conclude that this area that we estimated is actually 1. We can compute it, and then clearly the midpoint approximation is the best one here. In this problem we have to express the limit as n goes to the infinity of the sum k from 1 to n square root n squared minus k squared divided by n squared as an integral. So we have to interpret this sum as a Riemann sum for some function over a certain interval. In order to do this, the general term in the summation square root n squared minus k squared divided by n squared must be written in the form function value at some point times the length of a subinterval. And to see what function we might have and what our subinterval should be, the rewriting is necessary. We write sum k from 1 to n square root n squared minus k squared, and that divided by n squared equals sum k from 1 to n square root n squared minus k squared divided by n, and that multiplied by 1 over n. Here we have only written the denominator n squared in the form n times n, nothing else. But now we have the added benefit that this 1 over n is the length of a subinterval when the interval from 0 to 1 has been divided into n subintervals of equal length. Next, in the term square root n squared minus k squared and that divided by n, we move the denominator n under the square root, and we obtain that the original sum is now sum k from 1 to n of square root of the fractional expression n squared minus k squared divided by n squared, and that square root multiplied by 1 over n. And under the square root we may perform division by n, and we get that the original sum is now sum k from 1 to n square root of 1 minus k divided by n squared, and that square root value multiplied by 1 over n. And now this square root 1 minus k over n squared is the value of the function square root 1 minus x squared at the point k over n. And when we divide the interval from 0 to 1 into n subintervals of equal length, then these points k over n are endpoints of these subintervals. Therefore, this sum that we have to compute limit of is a Riemann sum for the integral from 0 to 1 square root 1 minus x squared dx. Hence, the limit is the integral from 0 to 1 square root 1 minus x squared dx. And we have solved our problem. Some comments are in order. We had to express the limit as n goes to the infinity, summation k from 1 to n square root n squared minus k squared divided by n squared as an integral. And we obtained that this is the integral from 0 to 1 square root 1 minus x squared dx. It is possible to compute this integral directly using calculus methods. The computation gets a little bit difficult and tedious and we do not yet have methods to solve this problem, or to compute this integral by calculus methods. However, we may make the observation that square root 1 minus x squared is a function whose graph is the upper half of a circle of radius 1 and center at the origin. That is the red curve shown in this picture. So integral from 0 to 1 of square root 1 minus x squared dx is the area of the blue domain indicated in the picture. So it is 1/4 of the area of disk of radius 1, and therefore the value of this integral is pi over 4, because the area of the disk of radius 1 is simply pi. And now we concluded that the limit as n goes to the infinity of the sum k from 1 to n, square root n squared minus k squared and that divided by n squared, is integral from 0 to 1 square root 1 minus x squared dx, and that this integral is pi over 4. In problem 5, we have to show that the integral from 0 to 1 square root 1 plus x squared dx is between 1 and square root of 2. We do that by observing that the integral from 0 to 1 square root 1 plus x squared dx is the area of the domain under the graph of the function square root 1 plus x squared and x between 0 and 1. The graph of this function is shown in this picture. It is the red curve. When x is between 0 and 1, x squared is also between 0 and 1, and therefore 1 plus x squared is between 1 and 2, and square root 1 plus x squared is at most square root of 2. Regardless what x is, x squared is always greater or equal to 0, therefore 1 plus x squared is always greater or equal to 1, and square root of that is always greater or equal to 1. Therefore, when x is between 0 and 1, 1 is less or equal to square root of 1 plus x squared, and that is less or equal to square root of 2. This means that the area of the domain under the graph of the function square root 1 plus x squared, x between 0 and 1, contains fully the rectangle whose base is the interval from 0 to 1 and whose height is 1. That is the rectangle whose upper side is the horizontal blue line segment. The area of this rectangle whose base is 1 and whose height is 1 is 1. Therefore, 1 is less or equal to integral from 0 to 1 square root 1 plus x squared dx. The inequality integral from 0 to 1 square root 1 plus x squared dx is less or equal to square root of 2, then follows from the fact that the domain under the red graph is contained in the rectangle whose height is square root of 2 and whose base is the interval from 0 to 1. The area of this rectangle is square root of 2, and that is why the integral from 0 to 1 square root 1 plus x squared dx is less or equal to square root of 2. This integral can be computed precisely using calculus methods, but it requires tricks that we do not yet know. Therefore, this area estimate is a quick way to get some kind of an idea of the actual value of the integral from 0 to 1 of square root 1 plus x squared dx. The function sine of t divided by t is undefined when t equals 0. Setting its value to be 1 when t equals 0 gives us a function which is defined everywhere and which is continuous everywhere. Therefore, regardless what x is, the integral from x to x squared sine of t divided by t dt is always defined. We define the function capital F by setting that the value of the function capital F at x is integral from x to x squared sine of t divided by t dt. And our task is to compute the derivative of this function capital F. We do that by using the fundamental theorem of calculus. But in the fundamental theorem of calculus, the variable of the function defined through an integral expression must appear in the upper bound of the integral only. Here the variable appears both in the lower and in the upper bounds. Therefore, we need to do a rewriting before we can apply the fundamental theorem of calculus. And the rewriting is the following. Capital F at x is by the properties of integrals. Integral from 0 to x squared sine of t divided by t dt minus integral from 0 to x sine of t divided by t dt. To compute the derivative of this difference requires the use of the fundamental theorem of calculus. By the fundamental theorem of calculus, the derivative of the integral from 0 to x sine of t divided by t dt is simply sine of x divided by x. To compute the derivative of the function capital G, which is integral from 0 to x squared sine of t divided by t dt, we must interpret this function as a composed function, where the outer function capital U is the function whose value at v is integral from 0 to v sine of t divided by t dt. And the inner function capital V is a function whose value at x is x squared. When capital U and capital V are defined in this way, then this function g of x is the composition of u and v. Therefore, we can compute the derivative of this function capital G using the chain rule. So, the derivative of the function f is now the derivative of the function g minus the derivative of the integral from 0 to x sine of t divided by t dt. The derivative of this integral is sine of x divided by x by the fundamental theorem of calculus. And the derivative of this function g of x is, by the chain rule, the derivative of u evaluated at v of x times the derivative of v. Now, the derivative of the function capital U is sine of v divided by v, and you plug in there v equals x squared. You get that u prime at v of x times v prime at x is sine at x squared divided by x squared times 2 times x, and then you must subtract from that sine of x divided by x, which was the derivative of the integral from 0 to x sine of t dt divided by t. So the derivative of the function f is 2 times sine of x squared minus sine of x divided by x. The function 1 over x squared always takes positive values. Therefore, one would expect that the integral from negative 1 to 1 dx divided by x squared would be the area of a domain, hence it would be positive. But if one computes the integral from negative 1 to 1 dx divided by x squared by the fundamental theorem of calculus, one gets that this integral is the integral from negative 1 to 1 x to the power negative 2 dx, and the antiderivative of x to the power negative 2, or an antiderivative, is x to the power negative 2 plus 1 divided by negative 2 plus 1. This is just minus 1 over x, and we substitute from negative 1 to 1. Therefore, we get minus 1 over 1 minus 1 over minus 1. Now there are many minus signs, and some of them cancel, and we get minus 2. And this, of course, cannot be an area because this is negative. So question is, what is wrong? And the answer is that this integral from negative 1 to 1 dx divided by x squared cannot be computed by the fundamental theorem of calculus. And this is because the function 1 divided by x squared is not continuous in the interval of integration, which is from -1 to 1. Therefore, this integral from -1 to 1 dx divided by x squared is really undefined and certainly cannot be computed by the fundamental theorem of calculus. Hence, this is wrong. The assumptions of the fundamental theorem of calculus are not satisfied. In problem 8, we know that the function small f is continuous and integral from 0 to x squared f of t dt equals e to the negative x squared, and our task is to determine the value of this function small f at 1. We need to differentiate the given equation to get a formula for the function f. Now let capital G of x be the integral from 0 to x squared ft dt. This function capital G is a composed function. The outer function u is integral from 0 to v ft dt, and the inner function is capital V at x equals x squared. So the derivative of g is the derivative of u evaluated at v of x times the derivative of v at x. The derivative of u at v is the function f at v. Plug in v equals x squared and you obtain that the derivative of g is f at x squared times the derivative of v, which is 2 times x. So g prime is f at x squared times 2 times x. This is using the fundamental theorem of calculus and the chain rule. On the other hand, we know that g of x equals e to the negative x squared. Therefore, g prime of x equals negative 2 times x times e to the negative x squared. So we have an equation. 2 times x times f at x squared equals minus 2 times x times e to the negative x squared. Therefore, f at x squared equals minus e to the negative x squared. And if x is 1, also x squared is 1, and therefore f at 1 can be computed by plugging in x equals 1, and we get f at 1 is minus e to the minus 1. So that is minus 1 over e. To determine the limit as x goes to 0 of the expression integral from 0 to x sine of t squared dt divided by x cubed, we have to use L'Hopital's rule together with the fundamental theorem of calculus. So L'Hopital's rule can be applied because at x equals 0, the expression whose limit we must compute becomes 0 divided by 0, so it is undetermined. Hence, the limit as x goes to 0 of integral from 0 to x sine of t squared dt divided by x cubed is the same as limit as x goes to 0 of the derivative of the integral from 0 to x sine of t squared dt divided by the derivative of x cubed, and this assuming that the right hand side limit exists. Next, we use the fundamental theorem of calculus. Derivative of integral from 0 to x sine of t squared dt is, by the fundamental theorem of calculus, simply sine at x squared. The derivative of x cubed is 3 times x squared. Therefore, we conclude that the limit as x goes to 0 of the expression integral from 0 to x sine of t squared dt, and that integral divided by x cubed, is the same as the limit as x goes to 0 of sine of x squared divided by 3 times x squared. That is 1/3 of the limit as x goes to 0 of sine of x squared divided by x squared, and this is 1/3 because the limit of sine of alpha divided by alpha as alpha goes to 0 is 1, and you may plug in here alpha equals x squared to conclude that the limit of sine of x squared divided by x squared as x goes to 0 is 1. Therefore, the limit that we needed to compute is 1/3.